of the Qubit by Qubit lab, section 3. I will wait a second for people to get on and I'll start sharing my screen. Great. So today we're going to be going over kind of a bit of review, I guess, and mostly just, I wouldn't call it review, like it says review in the slides a few times, but I'd call it more revisiting, kind of with being more informed of the context of why this math is important. Because we've covered a lot of the mathematics we're going to be going over today previously. However, we didn't have all the context for how it fits in with quantum information as well a few months ago. So we're going to be revisiting a lot of math. And to get started, I will, here's the attendance quiz passcode. I've switched to PowerPoint for today, so hopefully I will not have any technical issues with it. But we'll see, hope maybe it will go better than using like a PDF reader. I mean, I like the interface better for the other way, but we'll see how it goes. Yeah, this week we're just asking how useful your lab session is and the pace of the lectures. And I'd like to remind everyone that we cannot see individual responses on Canvas. So if you think that like everything's terrible and you hate everything about the course, then like just just give us feedback. We do want to improve, and there's no way that anyone will tie it to your response. Yeah, okay. So beyond that, I will also start the quiz for today on how comfortable you feel with this week's material, just to get like a pulse on where we're at. It's the usual scale. And yeah, and so I'm seeing a lot more 4s than usual. So we'll definitely like review a lot of the material that was covered in lab or in lecture this week. Oh, and I need to, one sec. I realized I have a bunch of notes I did not realize stayed on here. One second, let me stop sharing for a second. And you guys just continue with the polls and get Canvas dealt with. Okay, let me try to fix this. Okay. And if you guys want to put in the chat what you're most confused about from lecture, since there are a lot more 4s and 3s than usual, just feel free to do that and I'll address it. Okay, I fixed this. So I think we're good. Great. Okay, screen mirroring is back on. Okay, cool. Yeah, okay, so I'm gonna go over the I guess most commonly asked question from Piazza last week. And then I'll get into any questions you have about the lecture material. Although I may again, I might not answer them immediately if it's going to be in the slides, but I'm sure you guys have lots of questions that aren't in the slides. Cool. So the biggest question we got was, why are we learning Python at all? How is programming related to quantum information? Why should we care about this? And why Python specifically? So in general, most physics, I guess, programming is nowadays in Python. That wasn't always the case. Historically, back in the 80s, it was all Fortran. But nowadays, it's almost exclusively Python. And in general, the way that you control a quantum computer is you have a programmer that will automate the process for adjusting different parameters of your quantum system. You don't just you don't just like, I guess, like push buttons to have it do everything. You have to program it in for it to be efficient. So you do write code that, for a case of Python, is interpreted and then used to supply the electrical signals and the magnetic signals that you need to control the quantum computer. So for example, in my lab, we use this, we use a software that was developed by one of the PIs previously called Labber, that's now owned by Keysight. And it's all in Python, and it just automates all of the signal preparation. You might want different pulse shapes. You might want to do, like you might want to have feedback for, oh, I've put in a pulse, I got this result out that I didn't want. Let me adjust what I'm going to do next time. And you can add delays, do all kinds of things to actually control it. But that's very much on the like actually controlling what the quantum system is doing level, not on the circuit level or like a higher level. But with this, you can, like I said, you can get feedback with the output of the quantum computer, because one thing that is, I don't think we've discussed, but is really important about quantum computers is that qubits are really, really good sensors. That's why they are kept in like super high vacuum, super low temperatures. They're really sensitive to any magnetic fluctuations, to any electrical fluctuations, to any temperature fluctuations. It will be able to detect all of that. So if you put in a signal and it's not quite right, you will be able to detect that to a super high precision. So that's one thing that's super cool or like super convenient, I guess, and useful with quantum computers. And then specifically with this, IBM provides an interpreter for Python code called Qiskit, I believe. Oh, my pen is in red. Called Qiskit, that allows you to run both quantum circuits and quantum algorithms on both real quantum hardware that they have, and on simulated quantum hardware that behaves like the real quantum hardware would behave. And that's in Python, so it's very convenient to know Python. Oh, and I'm seeing the chat that people have asked if I'm going to be the TA for semester 2. Yeah, if you are in the same lab section, I will be continuing at the same time, the same place next semester. So yeah, but also you can switch lab sections if you would rather be in a different one. Yeah, great. So yeah, oh, and then also, so this is Qiskit, was this like IBM thing, but there's also a really common Python package called Qtip that people use to simulate different physics. And it's all written in Python. So there are similar things available in MATLAB, but I don't really know like if there's substantial infrastructure in place for other languages. I know R is commonly used for a lot of data analysis, but I don't know how common it is for like physicists specifically. But yeah, cool. So then this stack, or this thing that we previously discussed, I got rid of most of my random notes. Oh no, but not all of them. Oh, well, that's not going away. Well, it's fine. This thing is called a stack here, but you can also add extra layers to it with users. Like for example, if you want to do a quantum simulation for like chemistry, like quantum chemistry, you can have a chemist. And again, these photos, these are other TAs, Akshay and Alina, they're not just like random people we pulled. But yeah, so when this like programming of the quantum computer, this is, I'd say like this programmer in this case is mostly like automating things. And this, like the chemist is the user. So that's like really where we're going to be at, like for I guess all the discussions in this course pretty much is this is us. So we can give the programmer like a quantum circuit that we'd like to encode in like different pulses to send the quantum computer, and they can implement that circuit. or we could give them, like, if we wanted to simulate a certain Hamiltonian, we could give them that Hamiltonian and they could encode that. And I can go into detail on how you actually do that if you guys are interested in when we get to like more questions. Yeah, and yeah, and then I guess I've gotten a couple questions. Is a quantum computer stateless? I don't know what that means. What does stateless mean? And then a stack is just like the kind of, like people say like front end, back end, and like full stack when it comes to programming. A front end kind of deals with the user interface, and back end deals with like the actual infrastructure with how things work. And then you can have many layers in your stack if you have like different layers of user interfaces or whatever. So depending on what you're trying to do, like you'll specialize in different different areas of this, but for most PhD students, you do a bit of all of this. For more industry-like situations, you'd probably do one of these things. And a lot of times the programmer, if they're doing automation rather than coding, or rather than like high-level coding, you're probably also like working in like experiments with the quantum computer and like making sure it's all like functional and dealing with interfacing all the different instruments. So it's not just like, oh, I just automate things, I guess. Yeah, and I'm still like not, I'm sorry, I'm not like super experienced in like computers, or I majored in like electrical engineering, so I should understand computer science probably, but I don't. Uh, so I guess like any it sounds to me like I don't know if I don't think for the purposes of this, for what we're using these, like what we're using Python for, we're not really using like super low level aspects of Python. We're not dealing with like how it's actually implemented on the computer super heavily, even with this kind of automation control. It's still like higher level. So I don't know if we really care too much about like the intricacies of like the language. It's more like what's like flexible and usable, I guess. There's a lot of nice aspects to Python in particular because it uses like duck typing where you can have a variable. You don't have to declare a variable. You can just start using it. So there's just kind of some convenient like user things that make it intuitive for someone who's not like in the weeds with a lot of programming. Yeah, okay, cool. So yeah, so you think of this as translating to what you'd want to put into the quantum computer. And yeah, so that's the kind of intro for like why we should care about Python. Are there any questions about that or about anything covered in lecture? I know I got a couple earlier, but oh, okay. So I see one about the matrices, the polyrotation operators. So they, as far as I know, like weren't really derived ever. It was just like, oh, I want to do like this kind of rotation. And then probably just was like, I'll write it down. And he just like wrote them down and they happened to work out. And that's how a lot of physics honestly goes. Like, a lot of theory is like, this seems reasonable. I think it's reasonable that this would behave like a wave. So I'm going to write down this equation like it's a wave equation. And that's how we got the Schrodinger equation. So as far as I know, I think the Pauli matrices were mostly just kind of like written down. They do, they are useful for what we want to do with them. Like they were written down because they perform the actions that we want them to do, not because they are like super intrinsic to like you could describe the same action with like multiple other matrices, and like rotate your whole system and describe like just gotta have your basis be different and have your operations be different. So they're quite I guess fundamental, or like they're quite not fundamentally, they're quite like utilitarian, I think. And that's how a lot of this is. There's not like a super like a lot of things are not like derived, I guess. They're written down and then you plug them into the equation and see what you get out. Because in general, like the Schrodinger equation is a partial differential equation that varies with both time and position if you're dealing with like time dependent Schrodinger equations, and then you just kind of like write down what you think is reasonable, and then you get what you get. Great. So cool. If there aren't any more questions right now, I will start going into what we're covering for Lab 8. So we're going to go over Brock-Cat notation again, which we did discuss previously, including superposition states, normalization, and inner products. And technically, we did cover normalization before, but and these are all noted as review, I guess, except for this final bit for this measurement. And this is actually pretty quick, but I'd say I would describe this more as revisiting, because we've covered a lot more, I guess, quantum information, like quantum mechanics in lecture. And so it's useful to revisit things. And I always like to say, like, if you don't understand things the first time, don't worry about it. Because there's, like, to give a very specific example, there is a single paper that I have read about 20 times, like genuinely 20 times. And it's not a review paper. It's not like, oh, it's just like super big and like covers everything. It's the original theory paper for how a transmon, like a superconducting transmon qubit works. And it was written by like Jens Koch in 2007. And I have read it 20 times. Every time I read it, I'm like, wow, I did not understand this at all last time. And I completely misinterpreted like 4 points. I somehow did the math correctly because I just followed what they did, but like absolute disaster every time. And I always like learn a ton reading it again. So if you don't understand things the first time, just maybe get concerned if you don't understand it by the 20th time, but also it doesn't count if you learn it 20 times in like a week. It only counts if you learn it 20 times over like the course of a couple of years. And if you don't understand it after 20 times in a couple of years, then maybe get concerned and be sad. But until that point, like there's no reason to be concerned at all, because it is, a lot of this material is very complicated, and we are simplifying it because the course is aimed at high school students who don't have the same level of experience with a lot of these topics. Even if you have covered more advanced like mathematics or physics, you just haven't had as much time to think about it and like contemplate the meaning of everything that you're dealing with. So I really think that is super valuable. And I have some regrets with like how I did my undergraduate in 3 years and then did like a year master's program with it. And I kind of wish I just had longer to think about things before I had to start doing more complex stuff. But yeah, and the paper, I don't actually know like where it was published, but it's Koch 2007, and it's a transmon. Actually, I think it's called something like something Cooper pair box, not even transmon. This is like complicated. If you guys are interested, feel free to read it. I think it's Cooper pair box, something like that. And it's a great paper, but it is pretty complicated. And it is also very much like, I guess, hardware oriented. So if you're interested in kind of like the quantum information theory about like how quantum information propagates in different systems, it's completely irrelevant to that. It's the specific physics of how a type of qubit operates. So it's still like, it's much more like materials physics and a lot of superconductivity, but also like a lot of quantum physics. But yeah, it's still like an interesting topic. But yeah, okay. So now to stress everyone out, here is a diagram for a classical computer circuit, and it's obviously like massive, and who knows what it, I mean, you can look at it and pick out things that we did cover before. Like that's our NOT over here. I don't have an undo. This is why I don't use PowerPoint. So NAND, here's an XOR. And this, I think this is like a 5353, like old computer chip. I forget who made it, like Intel, IBM, TI, I don't remember. But one of those like old computer chips, it's like pretty complicated looking. I think this is some kind of like 4-bit register, but it doesn't really matter exactly what it is, or exactly how it works, because we are only going to deal with like this much of it, just as an example for how how to kind of understand and analyze a classical computer circuit, and then we're going to go into how that maps to a quantum computing circuit. So here is our little classical computer circuit that we just took out only part of it. And remember, we did go over this like months ago, so no worries if you don't remember it. But I will again just label these guys, because the names I think really help. You know exactly what they do if you know their name. Great. So we have this circuit, and we have our inputs here, we have our outputs here, and we can measure the output. This is a fully digital system, and a large part of this lab today is understanding how measurement and or how we interpret, I guess, the outputs of our measurements, and how we actually perform measurements on quantum computers. So with this, we put a bound. So I'll just draw like a little thing. We normally measure voltage. I guess we don't even need this x-axis. That's voltage. And we'll put like this will be like 1. This will be 0. And we'll just put a bound here and a bound here. And this is our dead zone, where if we get something here, we're like, we're just going to throw it out. That's invalid. But if it's up in this like top bit, that is our 1 zone, and down here is our 0 zone. And that's all you do to get your measurement state for a classical computer. And since we're going back to things, does anyone know what we would get as the output here if, let me just put in some like random, let's put a 1 here, a 0 here, and a 1 here. And I'm going to have to think through what this will actually do as well. But I'll give you guys a minute to work through it. And you can just do like one step at a time going through. So yeah, gotten one answer already. Nice. I'm getting a lot of answers. I'm impressed that you guys are so quick on this. So thank you to Diana and Dhruv and Rohan and Elon and Athena and Anantha Krishnan and Kenneth and Tomas and Padraig. Thank you all for all of your answers. I think you guys mostly have it right. But for those that couldn't quite get it through, so we have our 1, we go through our NOT gate, that gives us a 0. We end up with zeros coming into both of these inputs. This is our NOT AND. So if we, if it is AND, so if it's both 1s, we get a 0 out. And if it's not AND, so not both 1s, we get a 1 out. So this gives us a 1. So we have our 1 and our 1 coming into our exclusive OR. Since it's exclusive OR, it behaves like the English OR. So it's not exclusive OR. So we get our 0. And I think most of you guys got it right. I'm very impressed how quickly you guys got through it. So yeah, that's good on you for remembering how gates work. But yeah, they're all pretty straightforward, but definitely good to always revisit and remember how everything goes. Yeah, so now we're going to move to a quantum computer, where now we have a similarly like large circuit, but again, we're just going to take only a small part of it here. And so we have our input state, which could be anything coming in here. And I'm gonna work through this going up to this point. And we again have our measurement, and we'll go into exactly how this measurement works. later. I'm not going to draw like a cute little picture because it's a little bit more complicated. But if I put in a 0 state here, so this phi is a 0 state, do you guys know what you would get, I guess, at this point? So we're gonna ignore this thing, like, because I don't know what the other side is connected to. Same with these guys. Like, these are all, so you only really have these two gates right here, and this is a C naught, and this is a Hadamard. And you guys should have the matrices for these if you need them. But you can also kind of think through what they each, or wait, you can think through what the C naught does. The Hadamard, I guess I can give you, is 1, 1, 1, -1 over √2. Does anyone, I guess I don't expect you guys to necessarily be able to work through because you haven't done as much quantum gates as classical gates, but I'll give you another minute to think what you're getting through. And it's a little bit tricky because we're going into a superposition state. And then what I really want is the combined state, not just a single output. I'm getting some good guesses. So yeah, the C naught is also a gate. The C naught, oh my God, what does it do? It's, you have this first bit is your control bit, and your second bit is the bit that's going to be knotted. So I never remember how to actually like write out the matrix version, but I guess I can do it. I'll write a truth table first because I'm sure I'll get that one right at least. So if you have a bit 1, or I'll call it something else. Plus, I guess phi 1, phi 2, and then phi 1, phi 2. This is our input, this is our output. If we have zeros on both, then we get zeros out on both. And again, the first bit is your control. Oh, there's too much on this slide and I'm going to completely run out of room, but we're going to see if we can see it all, what it looks like. Okay, so then if we have a 0 on 1, but a 1 on 2, it again does nothing. But then if we have a 1 on 1, it will flip the second bit. So this stays 1, but this one flips to 1. And then this, sorry that it's like I'm writing over things, so I can't totally see it. And this gives us 1, 0. So the reason this is the symbol for the C naught gate. I don't know why it's not like a cute little box. Another color for the pen. I was told not to use red because some people can't see red on their screens. But I think it's all a lost cause at this point. I can't move text in PowerPoint for some reason, which I find very annoying. Let me see if I can, aha, keep. Yes, let me see if I can move it. I'm gonna move this down to here if I can. Oh my God. Haha, this might be better, maybe, okay. Great. Now I don't know how to get back into presenter mode. There we are. Okay, I've moved it. That's slightly better, maybe a little more readable. Great. So I've gotten some very good guesses from you guys. Thank you, Audrey and Nazar. I think, ooh, actually Nazar, you have it dead on. And Eric, you are off by a phase, but yes, you have the right idea. So what this is doing is when we go through our Hadamard gate, let me switch this to black. If we take a 0 state through a Hadamard, then this will give us 0 plus 1 over √2. And then when we do a C naught on that, and I can work through that in more detail if you guys want. This slide is just so small. Ugh, it's so hard to fit things. Oh, sorry, are you guys seeing a small screen? Let me make this, there we go. I don't know why the notes were open. Okay, great. Is that better? In vertical mode, oh, why? Better? Great, okay. Cool, so now when we go through our controlled NOT gate, what's going to happen is exactly what I showed with this truth table. I'll try to make it a little bit more readable. I wish there just wasn't so much on all these slides. I should have put less on the slides because I know I want to just write everywhere on them. But when we go through, when you're dealing with a superposition state, the correct way to think about it is not, oh, it's like it does one or it does the other. It's that it does both with some probability. So your output state should always have some component as if the input state was this and some component as if the input state was this. So what happens when you put in this 0 state, or when you put in this, I guess this is the plus state, is what you call it. So you can also write it like this. And you do a C0 with that as the control and the 0 state as the like flipped bit. What's going to happen is when you have the 0 state come in, your other input, your phi2, is going to stay the same. So I guess let's do plus comma 0 going into, I'll just write C0. That will give you a 0 state and a 0 state if you are in the probability case that your input from your Hadamard is 0. So again, this is over √2 because it's normalized. And then if you're in the 1 state, you can see, well, you can't see because I wrote it over top of things. Oh, I can't get rid of it, but I'll just write it. I'll write another line of it. If we have 1, 1, we get 1, 0 out. So, oh, and then actually it's this line that we care about anyway, so it didn't even matter. But if we have a 1, 0 input, so we have the 1 state coming in from our Hadamard, or our first input, so this is input 1, and this is input 2. Then we're going to flip our second bit. So our second bit started as a 0, but now we're going to end up with a 1 state over √2. And this is often written as 0, 0 plus 1, 1. This is the same thing. This is this is a tensor product state. Technically, these two states are both the tensor products of the vectors for each individual state. And I'm not going to go into that because the math is a little bit unpleasant, but this state is also a Bell state. And so this is an entangled state and the way that you can, I guess, demonstrate that a state is entangled is if you can't like separate the two components at all. Like if you know the state of one of the components, you know the state of the other component, then it's an entangled state. So an entangled state could also be 0, 1 plus 1, 0, because you know this, if you have the state of one of the two qubits, you have the state of the other qubit. Oh, and the plus is just this 0 plus 1 over √2. Yeah, so that's like, you guys don't have to know in depth like how this works. This is just a quick example of how one of these quantum circuits works, and we're going to go into a little bit easier ones in a second. But I just think it's a very fun little exercise, and this is one of the most important gate sequences in quantum information is creating a Bell state, because having this kind of entanglement is the really like important different thing from what you have with classical computation. Cool. So now we're going to go back into Braquet. notation. So we just did a bunch of kets and bras, but in case you didn't follow and we need to go through it, to remind everyone, the ket is just a column vector, and we define the 0 state as this 1, 0 column vector, and the 1 state as this 0, 1 column vector. If you're doing a bra, you instead just have you have the conjugate transpose of the same state. We often draw it as just like a backwards ket, or we always draw it as a backwards ket, and you get the column vector just rotated 90 degrees counterclockwise. And that gives you this output. Same with the one. The transpose, I guess, if you had a state that, let's say we have like this magical A state that's equal to I0, then the conjugate transpose of this would be negative I0. So when you take the conjugate, it does I to negative I and negative I to I for the imaginary number. So it's, I guess, functionally flipping the phase by 180 degrees, but only if it's like already 90 degrees out of phase. Like if you have a real number, then it won't flip anything. But if you have an imaginary number, then it will flip the sign of it. So yeah. And yeah, this is this Bra-Ket notation is what we use to describe all of our quantum states, and we use it to make clear that these states aren't just numbers, they are vectors on the Bloch sphere, or they are, I guess, probability amplitudes that are not, you don't just take the value of this state and be like, ah, yes, my result is equivalent to me putting in this value. It's a probability dependent on what values you may have put in. So if we have a superposition state, we don't get like half 1, half 0. We get a probability of 50% it being 1, we just measure a 1, and 50% of it being a 0, and we just measure a 0. So, and is the chance that a superposition will collapse to a certain state true random or pseudo random? It is exactly 50% chance that if you have a 50% superposition, you will collapse to 0, and 50% chance you'll collapse to 1. And for the sake of this, I guess I'm going to get into measurement in a second, but it's just so much more exciting than Bra-Ket notation. But the chance that like each thing happens is always going to be 0 or 1 as your options, because we always measure in the energy basis or the Z basis. That will only give you the option to measure a 0 or a 1. You cannot measure like a superposition state in a single measurement. You have no clue what state you have if you only measure it once, actually. You only know that you got a 0 at least once, but you don't actually know what state you're in. So cool. And then we'll go back to inner products with the Bra-Ket notation. So again, all of these states are normalized. So this is 1, or you can think of it as 100%, because this is only if the state, this quantum state describes your, like, I guess, full quantum system. Like, well, it doesn't have to be the whole system, I guess, in its entirety. But you need to make sure that each component is normalized. If you're only looking over like some subsection of your qubits basis, then you can have like not 1. But if you're in this, like, if you are looking over like the full basis of your qubit, you will always get 100%, because the probability that your qubit is in any of the states that it could possibly be in will always be 100%, so long as you have a qubit, and it will be 0% if you don't have a qubit. I don't know if that made sense. So these are probabilities. So the assumption is always that if you are contemplating something, it exists. So there's a 100% probability it exists. Therefore, the probability that is in a state of some kind is also 100%. So this describes all states of the qubit. And I guess, like, yeah, all, I guess, energy levels it's currently in, it's in one superposition state at any given time. But it always has a 100% probability that you're in one of the many energy levels that your qubit can have. And this normalization makes it really obvious that this zero, like zero broad cut zero is just one, because we know that it always has to be one. And we can write that out like we did before, and you can see, like, mathematically it is one. So yeah, and with that, and we have like a kind of brief example for like what this inner product actually means. So your inner product is the, we've defined it as, I guess, it corresponds to the angle between the vectors. So if you have, I guess, let's say AX, AY, and we'll say this is AX, AY, times, oh, I wrote this in the wrong order. We'll transpose BX, BY, where this is BX, BY, and our dot product is then AX, BX plus AY, BY. This is also equal to the absolute value of A times the absolute value of B times the cosine of the angle between them. So these inner products, when you are normalized, these are both one. So in the case of a quantum state, these are both one. So when you take the dot product, you're just getting the angle between the two states. And so you can see that with this like kind of more classical, like real life example, but it's also consistent with, or it's also like useful and informative for when you're in a quantum system. I've gotten a question about why the imaginary states are written as I square root 2, not square root I over 2. I believe square root of I is not well defined. I think you always want to have it be outside of a square root, but I'm not totally sure what the syntax is, like what the reason is for that syntax. But yeah, I can check on that and update on Piazza if I find something more useful than that. But yeah, so now we're going to do a quick little practice with inner products. So what is 0, 1? Put it in the chat. You should know immediately. Nice. So these states are orthogonal. They are exactly in opposite, or wait, yeah, they're exactly not in opposite directions in the block sphere, but they are in opposite directions in general. So they are 0. And this is, I guess, the basis we work on is orthonormal. And when you have the dot product of two orthogonal vectors, it's 0 in all cases. So it's like super, super easy. You know, if you have any of the states that we're working with, our basis states will always be orthogonal to each other. So if you take the dot product or the inner product of two different quantum states, you're always going to get 0. And so that's a really easy, like, you don't have to think about it at all, you just know it's 0. And if you have the inner product of the same state with itself, it'll always be 1 because it's normalized. So that's a really convenient like math trick. It makes all the math much easier for quantum mechanics in general. So now we have a superposition qubit state. where we have some probability amplitude, like alpha for the 0 state, and some probability amplitude for the 1 state, beta. So when we want to do that, we can create a state that operates like this, with alpha being I and 2 and beta being 2. Does anyone know what we'd get for this? And this is not a normalized state. No, it is. It is normalized. Okay. Yeah, so it should be easy to back out because it is normalized. Nice. Thank you, Becruz, Drew, Amog, Kenneth, Ariel, Rohan. Thank you, everyone. Yeah, it has to be normalized. So this did not go through that. I don't know. I thought I had the answer written down, but the result is if we have this times this, we have I negative I2. Wait, is that right? No, these are weights. No, that's right. Okay. I2. This isn't normalized. This is an unnormalized state. I totally thought that it was normalized, but maybe it's not. And this will give us. So I was actually totally wrong. And I totally lied to all you guys. I thought that this, because you have to take the conjugate transpose, you always remember to take the conjugate. We don't always have an imaginary state, so it's easy to get wrong. This will actually give us 1 plus 4. So this is not normalized. This gives us 5. And so what we actually want is to make sure to divide this by the square root of 5, such that it's actually normalized, and we end up with the state being equal to 1 when we take the inner product. So I completely lied to you guys. I read this wrong earlier. So if we take our normalized state instead, where we have 1 over root 5 negative I2 times 1 over root 5 I2, this will give us 1 over root 5, or let's just do 1 over 5, multiply them through earlier on. 1 over 5 negative I times 2, I times 2, which gives us 1 over 5, 1 plus 4, or 1. So yes, the mistake that I made when telling you guys what the state was and that it was normalized was that you have to take the conjugate of your cat, or your bra, yeah, of your bra. You can't just take the 2 with the transpose times itself, and that's like the real trick with these inner products, is that you always have to remember that it's the conjugate transpose, not just the transpose itself. But yeah, that is that's how you do a normalization, is you just want to divide through with the square root of whatever the magnitude of your resultant vector is. So it's a really quick way to renormalize your state. So yeah, okay. Now, oops, such a lag. Okay, so now we have a different superposition state, and this one is normalized. I'm very confident I'm not lying to you about this one, because this is the plus minus basis, and so this is a commonly used quantum state basis. It corresponds to being positive or negative along the Bloch sphere. So if this is 0, this is 1, this is plus, this is minus. And does anyone know what you'd get out for this? And this is normalized. I'm not giving you a trick question this time where it's secretly not normalized. This is as a trick, it is a orthonormal basis. I'm getting a lot of zeros, which is good. Yeah, so this is because these are two different states and we're in a orthonormal basis, we know it will be 0, but we can also work through it. If we have 1, 1, these are real, so we don't have to deal with the complex conjugation. 1, -1, that gives us 1, -1, or 0. So you can work through it, or you can just say, oh, I know this is an orthonormal state. I know that I'm working on an orthonormal basis. Therefore, it's 0 if I'm taking the inner product of two different states. Cool. So now, I forgot how much more I had to do. Oh, no. Okay. Well, we'll try to go quickly. So we can now express our quantum gates like we showed before with different matrices. So this is just like a little like hint slide. This is a square root naught, I believe. So it's the square root of a naught gate. A naught gate would not be reversible, but a square root naught is reversible. And all these X, Y, and Z matrices are the same as the Pauli matrices if you've seen them written like that before. And then this R phase it's a phase gate. It adds a phase to the 1 state. So you can see it will leave the 0 state unchanged, but then you'll get a 1 state times this e to the I phase. And so if you want to rotate around the Bloch sphere, you can do it like that. Like along the equator, you can do it with that. And the Hadamard is our entangling, or not, I guess it's not, it's like, it makes our superposition state, like it makes a 50-50 superposition. You want your C naught, I'd say like is more of an entangling gate. This is superposition. Or you can think of it as converting from the 0-1 basis to the plus-minus basis. And you can work through the math to like prove this to yourself. Great. So that's all of our quantum gates. You can just like look them up whenever you need them. So we can apply these gates to our qubits. So what we're going to do is give an example of applying a Z gate followed by a Hadamard gate to this initial state. So the first thing you want to do is find the column vector form of this state. Does anyone know what that would be? We actually saw it earlier. Anyone know what this state is? Oh, I can't believe I'm so close to out of time. We have so much more material to cover. Oh no, okay, whatever, it's fine. We covered some measurement earlier. Okay, no one knows this is just the 1/√2 I2. That's our column back, or sorry, not 1/√2, 1/√5. I'm too used to writing 1/√2. This is 1/√5. So that's our column vector form. I'm just going to write it on every slide because I did not decide to write it out on the slides. So what we want to do is, for step 2, is we want to multiply the matrices of the Hadamard gate and the Z gate. And so we're applying the Hadamard gate first, and then the Z, and then the we're applying the Z gate first and then the Hadamard gate. And the way that we do matrix multiplication is we always start from right to left. So we actually would have our state and then our Hadamard and then our Z. So the first step is to do this operation. And so this gives us 1, 0, 0, -1. This gives us 1, 1, 1, -1. And the result of that is we multiply through with the dot product. So we get 1 times 1 plus 1 times 0 gives us 1. 1 times 0 plus 1 times -1. Gives us -1. Wait, did I do this right? 1 times 0, 1 times 1 plus -1 times 0 is 1. And then 1 times 0 plus -1 times -1 is 1. Okay, that's right. This is the resulting matrix for our Hadamard times our z. And so now what we want to do is we want to do the final resulting matrix. That was our 1, 1, negative 1, 1 times our square root 5, I, 2. With all these, you always, like matrix multiplication always, I guess, happens right to left. So the thing that exists first, like when you're drawing it out as a circuit, like this is our input is here. We go through a gate, or I always keep clicking that. Our input, so I'll put like here, is connected to a bunch of boxes, and that gives us our output. But when it comes to matrices, you have your input times, so I'll call this G1, G2. This is G1, this is G2, and then the result is your output. And this is just how matrix multiplication is defined. Oh, and that was a very good point. I did not normalize my gate. There should be a 1 over root 2 for a Hadamard, and on this previous slide here, this Hadamard should have a 1 over root 2 in front of it. It's important to normalize your states. You can always like not normalize anything and then just normalize at the end, because your vector will always be pointing in the right direction. The magnitude will just be different. So you can not normalize anything until the end if you don't want to. But you just have to make sure to normalize it at the end if you want to have it like be consistent with what you'll see like written down. But it's also a lot easier to do math if everything's normalized, because you know that everything's either a 0 or 1 pretty much. So I'd recommend just normalizing everything, but if you forget, it's like not that big of a deal. So now I multiply this through, and that gives us 1 over root 10 times I times 1 plus 1 times 2. This is I plus 2, I times negative 1. Did I do this not in the right order? This seems not right. Let me think for a second. No, okay, I know where I went wrong. I have my signs off. I was like, this is definitely not right. This should be a negative up here, because and that should not be negative. Because what we're doing, this is why I hate multiplying matrices by hand. I like to do them on a computer because then I can't do them wrong. But we multiply this one by this one, and again, and this one by this to get this location. Multiply this one by this and this one by this to get this. I feel like I've done this wrong still. But I know I'm supposed to get a negative 1 out on the top. Okay, well, we're just gonna move forward, and the algebra doesn't matter that much. The point is that this is kind of the process, and it's very easy to do things incorrectly. But this should give us a negative up top and a positive on the bottom. I swear I went through this like 4 times earlier today, and I had it right, and now I don't know where I'm going wrong. But I will correct it before the slides are uploaded to Canvas. So if anyone needs like more detailed version, you can see it there. Okay, so this is our resulting state. And that's just how you do like a multiple gates in a sequence. So are there any questions on the content so far? And then we have a bunch on measurement that is very important, but I am just like out of time. So if you have to go at 9, no worries. We'll be covering quantum measurement, but this will be uploaded onto Canvas, so you'll be able to watch it on your own time if you're interested. And I already discussed a lot of measurement stuff earlier that we're not going to go too much more in depth because I kind of spoiled a lot of the measurement stuff. So cool. The Z on the right, maybe it's possible I have something. Did I do, wait, did I tell you? Yeah, okay, oh my God, okay. Yeah, no wonder I had this wrong. I told you which order you're supposed to multiply them in, and I did the backwards. So this should be, in fact, Hadamard and then Z, not Z and then Hadamard, because Z is going first. So I wrote out the general equation correctly, but unfortunately I don't know how to do. I think the issue is that it is the Z gate and Hadamard is a better way of writing it, because the Z gate is happening first. You do want to multiply like H times Z, I guess, if you're like writing, like if you're talking about it from left to right, but it is this order. And then this should all work out. Yeah, now it works. Okay, great. So I can't do algebra. I'm sorry to everyone for having to witness my terrible algebra. I'm going, like, I genuinely, like, I went through this and I still did it wrong. So in the future, I will just open up like a terminal window and like type into Python, and then it will tell you the results, because I'm incapable of doing it by hand, because I always do it on a computer now. But yeah, if there aren't any questions, I will go through the measurement stuff. So now we've expressed our quantum gates, and the important like final step is when we want to measure our states. This is, we're gonna be talking all about measurement. So when we're measuring a classical bit, like we discussed earlier, we measure it, we measure it 1, we get a result 1. And we do that with kind of splitting up our voltage into our 1 region and our 0 region, and defining these as, and this is our dead zone. And so it's deterministic. You will always end up with the correct, or you will always end up with the correct value as long as you're not in this dead zone. And there's no probability that you end up with a 0 if you're in the 1 state, or like, it's designed such that you will never end up in this. I've gotten a question from Clark, if you don't need to know algebra to be a physicist. So the funny thing is that algebra has nothing to do with math. Like, you don't have to do any like numbers. It's all like kind of very theoretical, like groups, like different types of groups and different like more like, I guess, high level math where you're not writing out numbers ever, so you don't have to deal with numbers very often. You do have to deal with numbers on like exams, but eventually you stop having to take exams and then you forget how to do math, and no one notices. So yeah, don't worry if you can't do math by hand. It's like, there's certain stuff that's important, but actually getting like the right numbers going through is not that important for physics. It's very important for doing more engineering, which unfortunately I do quite a bit of both. Yeah, okay, so then in our 0 state, these all are deterministic, which means that there's like a 100% probability that like you know your state with 100% surety if you've measured the state to be one of these two values. You know that if you measured a 1, you are in state 1. If you measured a 0, you're in state 0. So we'll write that out because I think it's an important note. Okay, so now for measuring a quantum bit, we can still do the same thing where we've measured, we have our output state is 1, we measure it, we see that we're in the cat 1, and output state 0, we measure cat 0. But what is that actually, that's if we are in one of these two states. This is actually like 100% times this and 100% times this. If we're in a superposition state where we're in, I guess if we say this is like 0.6 1 plus 0.40, what do we get out? What are we going to measure with this? And I guess it's a little bit of a trick question the way I framed it, but does anyone want to guess what we're going to get? Oh, yeah, you guys are right. This needs to be a square root. Yeah, always normalize your states, kids. Oh, that's not right, actually. This should be square root 2. Why can't I cannot do math this time of night, clearly. This should be over root 2. There we are. Great. Yeah, so if no one wants to guess what this will be, I can tell you that it's 60% 1, 40% 0. So what that means is you have to measure it a bunch of times. You have to, like, if you want to like have a reasonable guess at what your probability, what your superposition state is, you probably have to measure it like 15 times, 100 times, whatever. You can't just measure it like one time. So that's kind of the trick with all these quantum measurements, is you don't just measure them once. You can't, since they're not deterministic, they're probabilistic, you have to get the probability of what state you're in. And actually, no, is this, no, you are right, it should be, so again, I can't do math this time of night. Yeah, it should be screwed, because it's, the resulting state is the absolute value squared of this plus the absolute value squared of this. So we want these to be the square root of each, and the sum of these two be here. I'm too used to writing superposition states. I know this. Okay, stop asking me questions about how math, like how algebra works. I don't remember. I know this is right, and this needs to be equal to 1. So each section of your superposition is squared, and that's because these are probability amplitudes, not like probabilities themselves. So an amplitude is the square root of the energy. That's kind of language borrowed from, I guess, a lot of different fields, but a lot of it's like engineering. If you're dealing with like RF engineering, the amplitude of your signal is the square root of the energy of your signal. Yeah, okay. So that's what the superposition state is. If we're here, it's a similar thing. Does anyone guess, if I say, let me say this is like, I don't know, 0.4, I'm gonna normalize it correctly, plus 0.6, or wait, no. Why did I write this? 0.4 of 1, 0.6 is 0. Does anyone know what we're going to measure here? Nice. Yes. That, like we said on the previous slide, it's going to be, I wrote this super unclearly. I'm sorry if any of you get it backwards. I know what you mean. This is, yeah. Let me do 0.6 of the 0 state plus 0.4 of the 1 state. Cool. Yeah. So the results of this state is going to be, the result of this measurement is going to be 40% chance it's one of these, and then 60% chance of the other one. And that's how all these measurements are. Like, you have to measure it multiple times to actually get the right value for the superposition. Cool. So the results is the square of each of these factors. So if we had, I think these are in the wrong order, but if this was 0.8 and 0.6, which 0.8 squared is, oh my God, 0.64, 0.6 squared is 0.3. Oh, that works out. Cool, great, love that. Yeah, so this is, I guess, if this was 0.8 and 0.6, then this is 0.8 squared, which is 64% being in the 0 state, and this is 0.6 squared, which is 36% of being in the 1 state. And so that is an easy way, or guess like it's pretty simple once you know like what the right way to do it is, but that's how you get these results. Cool. Oh my God, for some reason this keeps lagging. So we have, obviously we have covered kind of the basics of how these measurements work, but we haven't discussed why we only measure a 0 or a 1. And I did say we measure in the energy basis. Technically, like we can measure in other bases where we perform rotations to project the measurement from like a plus state or a minus state into the energy basis and then read it out and be like, oh, I just did an X basis measurement. But we are like fundamentally, we are measuring a 0 or a 1 always. I think there is like, there's research going on for everything. So I think that's not like, it's possible we're not necessarily limited to that, but functionally we are limited to that for now. And so that kind of, you can project from different bases. Using gates, like going from the equator up to the positive or like negative axis, like the z axis. You could do like a Hadamard, or depending on like what you're trying to do, like an X and then like half a Z. Like there's different pulse sequences you could do. What is the state of the qubit after the measurement? And these are very like rough, quick descriptions for like kind of what we're going to cover without any detail. So what's the state of the qubit right after the measurement? It's whatever state you measured. So if you were in the 0 + 1 over √2 state, then, and you measure a 0, then the qubit is now in the 0 state. It's not in the superposition state anymore. Your wave function has collapsed and you're in the state that you measured. However, the state you prepared is not that state. You prepared a different state. So that is an important point. Why this happens is there's a lot of interpretations for why this happens, what it means, all of that, but it's not like I guess a close, like it's still an open question of like what exactly is the best way to interpret this. And then what would you get if you measure the qubit twice? You get the same thing twice. And that's because you have projected your quantum state into whatever basis you measured in, and you've projected it into a certain state, and then it's that state now. It doesn't change. So I think that's all of the, I have like kind of a review slide, but I'm going to start the poll for the end. Oh, that's not that. I'll relaunch this poll. And let me know like how well you understood. I did cover a lot more advanced topics, so no worries if you didn't follow all of them. And yeah, there's, I guess there was a question on how long it takes quantum computer to perform a calculation. It depends on what calculation you're doing, but you don't measure the quantum state after each step. So what you do is you prepare a quantum state, you know that you've prepared the state like well, and then you will perform a bunch of operations on a bunch of gates, and you won't measure it at all. And those gates are pretty fast, on the order of like nanoseconds. Normally your coherence time, which is how long you can retain a quantum state, is on the order of tens of microseconds. So all of your computations have to be completed for like a certain state within that time. Otherwise, you lose your state. Yeah. So we are quite a bit over time. I don't want to keep anyone any longer. If you guys have any more questions, you can ask me on Piazza. Yeah, sorry for going over. I completely did not pay attention to how long I was spending rambling about measurement earlier on. But yeah, thank you everyone. I hope that this was informative. I hope I didn't go too far into like the weeds, but we're going to cover a lot of this a lot more in depth next semester. So if you don't understand it now, that's intentional. You're just hearing about it for the first time, and then in like a couple months, you'll understand all of it. Yeah, great. Thanks everyone.